and the subject is derived geometry. So, Jacob.
Oh. Well, I don't know exactly what you would like me to say. Maybe it makes more sense to take questions.
Let's start by, so what is derived geometry? What it does?
What?
The chart. That's right. He has this result where he says, well, we have cobordisms. Like a derived manifold looks like locally like the 0 section. You take a section and you take the 0 section of a.
So, all right. So by derived geometry, you're thinking of like smooth manifolds rather than algebraic geometry.
There is a smooth version, and then I guess there is a algebraic geometry. Yeah.
Okay. So let's talk about the smooth version. So let's suppose I give you a smooth manifold M. Now, let's suppose that I give you two N0 is codimension D, and N1 is codimension D0, and N1 will be codimension D. So now if N0 is transversed to N1, then you can form this intersection. If N0 and N1, it's a subset of M, and that'll be a submanifold of codimension D0 plus D1. And moreover, you can say what this intersection is doing at the level of cohomology. So these N0 and N1 determine classes, cohomology classes. The class of N0 and the class of N1 the class of, let's say, the class of Ni lives in the cohomology of M in dimension di, let's say with z mod 2 coefficients, so that I don't have to worry about orientations. And similarly, there's a class of, in this situation where they're transverse, you can look at the class of the intersection of these two submanifolds. This is a cohomology class of degree d0 plus d1, and in the cohomology ring of M, it's the cut product of the class of N0 and the class of N1. So this, I don't know, let's give this a name. Let's call this the intersection formula. Right, so the cut product on cohomology is kind of designed to make this statement true. You want an operation on cohomology classes that matches with your notion of intersecting submanifolds. And this is a sensible statement to make as long as N0 is transverse to N1. In that case, this is a submanifold of M having the right dimension. But so if N0 is not transverse to N1, then the intersection of N0 and N1, if we're working in the setting of smooth manifolds, you can't really say anything about that. You can't say it's a manifold, or it could be a really horrible subset of M. So it could be something where you had no reasonable notion of dimension. And a priori, it's something to which you have no reasonable guess as to what cohomology class you should assign to. So you asked the question, what does derived geometry do for you? Well, derived geometry, one of the things that it does is it gives you a correction to this. It gives you some way of making sense of N0 intersect N1. You don't just keep track of that as a subset of M. You keep track of some extra data, and that extra data remembers somehow that this intersection is supposed to be something of dimension of M minus D0 minus D1, and it remembers enough that you can recover a cohomology class associated to this intersection, which would satisfy this formula.
in the case in which there was universality, for some nice coincidence, just the set remembers the smooth structure.
I guess the set as when it's embedded in M, if you just remember the set as a topological space, it wouldn't.
No, but the subset of M remembers the smooth structure.
Yes.
But here, you have to use the simplicial methods to tell me what the smooth structure of the intersection is. A little bit like they used to do with the cotangent complex or something like that. So how does it work here?
So I can tell you how I would set up the theory of these. Thank you. All right, so let me give you a definition of what I'll call a derived manifold. So it's going to be a certain mathematical object, and it's going to have the feature that even in the non-transverse case, I can regard n0 intersect n1 as an example of this kind of mathematical object. So this definition should be more or less the definition that's in Spivak's thesis. Okay, so it's going to be a definition in the style of algebraic geometry. So I'm going to, I want to contemplate pairs, which I'm going to call x, OX. So here X is going to be a topological space. And OX is going to be something that I'll call the structure sheaf of X. Now, if I'm working in the setting of smooth manifolds, OX, I don't want to think of it as like the sheaf of real valued functions. I want to remember a little bit more data. What I want to do is remember what I mean by smooth map from X into smooth manifold. So OX is a, I don't know what notation to use. So this is going to be, this is going to be it's really a functor of two variables. So OX is a construction, an open subset of X, and it takes a smooth manifold M. Let's say you have an open set, which I'll call U, and a smooth manifold M, and assigns to it a space. And here, when I say space, I mean in the sense of homotopy theory. I'm interested in the homotopy type of this space. So here I'll assign to U and X something that I'll call OX superscript M of U. And what I want to think about this as the space of smooth maps from U and M. And this should be functorial. It should be a contravariant functor of U. That's why I wrote this op here. I can, if U contains a smaller open set V, then I can take a smooth function from U into M and restrict it to get a smooth function from V into M. And it's covariantly functorial in M. In the sense that, if I have a smooth map from U into M, that's in quotation marks, and I have a smooth map from M into some other smooth manifold N, that's not in quotation marks, I should be able to compose them and get a smooth map from U into N, again in quotation marks.
What are conditions on M?
What's that?
What are conditions on M? Not necessarily.
Oh, M, any smooth manifold. Any, yeah.
How's that?
What's that?
How's that?
It doesn't matter. I mean, I'm going to throw some axioms in, and the axioms will have the effect that it's not, the notion will be insensitive to exactly what class of smooth manifolds you allow.
Second question, so space of smooth maps, we shouldn't think of the space of smooth maps with any kind of topology naturally, or...
Right. So the classical, so here's the usual example. Is X is a smooth manifold. And then OX superscript M of U is the collection of smooth maps from U into M, and this is just a discrete. So this is how you regard an ordinary smooth manifold as in the world that I'm going to describe.
With the discrete topology.
With the discrete topology, exactly. So this space, I mean, the sense in which this is derived is exactly that I'm sort of turning on homotopy theory here by allowing
Simplicial sets or something.
simplicial set. Yeah, so simplicial set is probably a better thing to say than space, because space might make you think, oh, you're looking at the C infinity topology on some mapping space or something like that. That's not what it's meant to encode here. It's meant to encode that you're doing some kind of homotopy theory. So simplicial set or Kahn complex is a good model for what you're doing here. So I want to write down some axioms that you could require of an OX that, that will be satisfied in this basic example, and will be the so first axioms for OX. And so the first axiom is that, well, if M is fixed, then you look at the construction U goes to OXM of U is a sheaf on X. And when I say sheaf, maybe I should put a little star here. Sheaf means what some people would call a homotopy sheaf. It means it satisfies a sort of higher categorical version of the descent condition that usually specifies what it means to be a sheaf. So what this means is that, i.e., if U is covered by open sets U alpha, then if you want OXM of U, you can recover this as the homotopy limit of OXM of V taken over all V that are contained in some U alpha. So you can recover the space of maps from U into X by knowing, to make a map from U into, smooth map from U into M, you just have to specify it on small open subsets of U, where small means contained in some open set of a cover. Yeah, and this is a homotopy limit. So if you wanted to turn this into a very precise definition, you could say OX is going to be a functor from literal sense from this category across this category to the category of simplicial sets. In the category of simplicial sets, you have a notion of homotopy limit, and this map should be a homotopy equivalence onto the homotopy limit. Okay, so that's an axiom. So let me summarize this informally. This is the axiom that OX is a sheaf. This is saying that OX has good behavior as U varies. So axiom 2 is, I'm going to put this in quotation marks. This is the condition that OX is local. So this is going to be a condition about what happens as M varies. So if M is a smooth manifold, has an open cover by submanifolds M alpha, so then for each of those open submanifolds of M, you have an OX M alpha, which by functoriality maps to OX of M. So you could take the coproduct of all of these maps And this map should be, let's say, a surjection of sheaves. And what I mean by that is that if I give you any point of OXM of U, then after passing to an open covering of U, you should be able to promote that point to a point. Any map from U into M locally on U factors through one of the M alphas. That's the intuitively what this, or I mean literally what this means.
What's the notion of surjection for simplicity's sake?
So what surjection on pi 0, but well, it's in the sheaf theoretic sense. On stalks, it's surjective on pi 0. Yeah. And then axiom 3 is another axiom about what happens as M varies. So there's lots of equivalent formulations, but let's say if you have a diagram of manifolds like this, M0 mapping to M, M1 mapping to M, and let's suppose that, say, M0 mapping to M is a submersion of smooth manifolds. So then you can form the fiber product, and this condition that this map from M0 into M is submersive guarantees that you get a smooth structure on the fiber product. So if you're in this situation, in reality, you have a map from O M0 cross over M with M1, let's say evaluated on any U, maps to OX M0 evaluated on U. U maps to OX M of U, and then you demand that this is a homotopy Pollak square. So this is saying if you want to give a map from U into this fiber product, then you just have to individually give a map from U into M0, a map from U into M1, together with some compatibility of the induced maps from U into M. And you demand this axiom only in the case where the fiber product is something you expect to be well behaved. So, yeah, for example, when M0 to M is submersive.
What's that? I mean, saying that it's a homotopy fiber product in the world of sheaves is the same as saying that for any U, it's a homotopy fiber square of spaces when you evaluate it. Okay, so these are the three axioms for OX that I would like to write down. I'll start erasing them.
So definition, I don't know what to, well, I want to add the word generalized. Generalized derived manifold. Is a pair XOX satisfying these axioms. Okay, so if you look in the world of generalized derived manifolds, these can naturally be organized into an infinity category. In other words, when you work with objects like this, you're doing homotopy theory. Between any two generalized derived manifolds, you can define a space of maps. And the world of smooth manifolds, the usual category of smooth manifolds embeds fully faithfully into here. Any smooth manifold can be embedded, can be regarded as...
This is all simplicial maps, or why?
Yeah, so you want to know what the maps are. Okay, so let's say that I give you an XOX satisfy these axioms. A map, well, map F is a pair consisting of, first, F0, a continuous map of topological spaces from X to Y. And then alpha, which is going to be a, I don't know which way, I guess it's easier. Well, F0 upper star OY to OX. So here I mean to sort of pull this sheaf OY back. So it's a map of sheaves or sheaf-valued functors on the category of smooth manifolds. And alpha has to satisfy an axiom. Again, this is modeled on the in algebraic geometry. So in algebraic geometry, the notion of a map of scheme is given by a map of the underlying topological spaces, a map on sheaves of functions, and this map has to be local. So the analog of that condition here, such that it has the following property that if you, let's say, if you have a map of smooth manifolds n to m, which is an open immersion, then, well, F0 upper star OYN maps to OXN, and it maps to F0 upper star OYM, which maps to OXM. You just get this diagram for free by functoriality, and you demand that this is a homotopy pullback square. So let me say in words what this is saying. So this says the following: if you have a map from Y or some open set in Y into M, you can ask whether it factors through N, and that happens on an open subset of the domain of your map. And this says that that open subset behaves well when you compose with this F. If you want to know, if you had some map from Y into M, and you're wondering when does it factor through N, well, there's also, if you compose with this F, you get some map from X into M. There's some open subset of X where it factors through N. The open set here should be the inverse image of the open set here. That's, anyway, it's a natural demand to make, and it's the only demand that you need to make in order to guarantee that the category of smooth manifolds embeds fully faithfully into this world of generalized derived manifold. Or actually, if in the definition if you set up the definition so that OXM is defined for any smooth manifold M, then it's probably very easy to check this. But to answer your question earlier, which M's do you allow? Once you've imposed these locality conditions, both on the sheaf and on the maps between sheaves, it has the effect of not mattering which, as long as you allow enough smooth manifolds, like smooth manifolds that are homeomorphic to Euclidean space, then you'll get the same answer.
You get generalized manifolds which are really very generalized.
Yeah, so this is like the analogous in algebraic geometry to the category of locally ringed spaces. And so if you want something that's more analogous to the category of schemes, then you want to introduce some additional restrictions. So let me introduce one which is convenient.
For example,
Yes. No, but it's a bad idea if it's not C infinity. Well, maybe you don't see it at this level. Right. So let me make a remark about that. All right. So I told think of OX as a structure sheaf, but it's a structure sheaf in maybe not the usual algebraic sense, because it's not a sheaf of rings, right? But it determines for you a sheaf of rings if you decide that you want to extract from OX the sheaf of functions with target R. Then you can add R-valued functions, you can multiply R-valued functions. So this is a sheaf of, well, if our target was sets rather than spaces, this would be a sheaf of commutative rings. But since our target is spaces, it's a sheaf in some more general world. So this is a sheaf of, let's say, simplicial commutative R algebras. So now you could ask, how much information is lost by taking this sheaf OX and remembering only this sheaf OXR? And the answer is some information is lost, which was exactly the point of defining things in this way, right? The sheaf OX, the sheaf OXR, it remembers what the real value, to some degree of approximation, not much is lost for the following reason. So the way OX is defined, the axioms that we imposed on it, guarantee that if you want to know what OXM is, it suffices to know OX for some nice covering of M. And M is a manifold, so it suffices to know what OX of Euclidean spaces are. And OX commutes with, as a functor of M, it commutes with products. So if you know what this is, you should know what OX of any Euclidean space is. But that just tells you something after you've made a bunch of choices. If you want to sort of canonically reconstruct this object from this object, you can't do it, because this object only remembers that you can add and multiply real valued functions. This object remembers real valued functions, and it remembers that you can compose them with other smooth functions from R to R. And okay, so this process loses information, but it doesn't lose very much information in the following sense, that in many cases, if you want to perform categorical constructions on these objects, like if you want to form a push-out diagram or something like that, then this forgetful functor will commute with that. So in other words, if you want to form certain tensor products in the world of these kind of structure sheaves, if you just want to know concretely what's going on, you can reduce it to a question about forming tensor products in a more familiar algebraic world. And the ability to carry out that reduction only works in the C infinity case. It would break down in the C2 case.
Well, it's kind of clear if you want to compose this infinity match from R to R anyway, because Cn is not really closed on compositions. When you compose, you lose
Cn is closed on composition.
well, okay.
I think that, I mean, the issue is, well, I don't know, maybe we're getting into something too technical. Anyway, define for you what the notion of map is here.
So, for example, the free loop space of a manifold is there.
Well, it depends on what you mean. Well, let me make a remark about. So theorem, is that this world of generalized infinity category of generalized derived manifolds has fiber products.
Oh, okay, it has fiber products.
It has fiber products. Now, the world of smooth manifolds doesn't have fiber products. So what happens? So suppose that I gave you
You don't need submersion or anything.
right. So suppose I gave you a diagram of smooth manifolds like this. Now, in general, if these maps are not transverse to one another and you try to form some kind of fiber product, you will leave the world of smooth manifolds. Now, the definition of generalized derived manifold is rigged so that First, there's a fully faithful embedding like this. And second of all, it preserves all the pullback squares that you have in the category of smooth manifolds for good reason. It preserves all of the squares where, let's say, one of these maps is a submersion. Or it more generally preserves the pullback squares where they're transverse to one another. So in the case where these things are transverse, so that this thing is a smooth manifold, that's how you also form the pullback in the world of generalized derived manifolds. But in the case where these things are not transverse, then the fiber product, you can form a fiber product here, and you'll get an object which is usually not going to be. In fact, I guess if it's not transverse, it will never be a smooth manifold. So this is just one of these generalized objects.
Well, it could be the set.
Yeah, so for example, here's a situation you could consider. R, let's say 0 goes into R, and 0 goes into R. And here's a diagram of smooth manifolds that does have a fiber product in the category of smooth manifolds, but the maps are not transverse. So that's a pullback square here that is not preserved by this inclusion. If you form the pullback in the world of generalized derived manifolds, you won't get just a point. You'll get a point with some funny structure sheaf attached to it.
Could we see that example?
Yeah.
What structure sheaf we have?
OK, so I'll tell you what you have to do. OK, so this is going to be some XOX. And let me tell you how you build XOX. So first, X as a topological space is just the usual fiber product. So X is going to be the set consisting of just 1.0. And now what is OX going to be? Well, let me call this map F, and this map G, and this map H. So this OX, whatever it is, it should receive a map from F upper star of the structure sheaf of 1 point. And it should receive a map from G upper star of the structure sheaf of 1 point. Now, since F and G are just the identity map on the level of topological spaces, I can sort of erase this F upper star and this G upper star. And it should receive a map from H upper star of the structure sheaf of R. And this should be a push-out square in the world of the kind of structure sheaf that I'm describing. And now we exactly meet the issue that I was talking about in response to your question. If you want to actually know what that push-out looks like, you can't hope to compute it if you work with C2 manifolds or something like that. In the C infinity case, you can actually describe what this looks like because it will remain a push-out square when you sort of forget most of the structure and just remember that these are sheaves of algebras. So what happens in this case? So this H upper star, so these three guys are just, now I'm talking about sheaves of ring. These three guys are just ordinary rings, and this guy is going to be some kind of a simplicial ring. So what are these rings? Well, this is the ring of real valued functions on a 1 point. Or in other words, it's just the ring R. And this is the ring of real valued functions on 1 point, which is again just R. This is what you get when you take the sheaf of smooth real valued functions on R and pull it back to a point. So this is the ring of germs of maps, smooth maps from R to R at 0. OK, so now you have to so let me give this ring a name. Let me call it A. So let's say now you want to, so this OXR is going to be given by forming this push out in the world of simplicial commutative rings. So OXR is, what's that? Same as DG rings, yeah. We're in characteristic 0, yeah. So you're supposed to form some kind of left-derived product of R with itself over A. OK, so how do you understand this left-derived tensor product? Well, you have to view R as an A module, and then you want to resolve it. Choose a projective resolution of R by A modules, and then tensor that projective resolution over A with R. well, it's really simple in this case, and here you'll see why it's essential that we're using C infinity functions. So first, what is R? R, it has one generator as an A module, namely the element 1. That gives you a map from A into R. And now what's the kernel of this map? This is the kernel, that's the ring of germs of smooth maps from R to R, germs at 0 that vanish at 0. And in the C infinity world, that's just a copy of smooth maps from R to R at 0. Like if you have a smooth map that vanishes at 0, you can divide it by x, and you get another smooth map from R to R. Now, if you were in the C2 world, that would be bad because you would take a C2 map, it would vanish at 0, you'd divide by x, you'd only get a C1 map back again. But in the C infinity world, you have a short exact sequence like this. And then how do you form this tensor product? It's given by, so this chain complex is quasi-isomorphic to R. So if you want R tensor over R with A, you take this chain complex and you tensor it with the real numbers, which gives you this chain complex where here x is 0. So you get, so what that means is that the real valued functions on this fiber product a real valued function is not just a real number. Now, there's a space of real valued functions. Pi 0 of that space is the real numbers, and the fundamental group of that space is also the real numbers. And this, thinking about that space, it remembers that when you look at this diagram, so if this was transverse, you would expect the codimension of this in R to be the sum of these codimensions. So the fiber product object, it wants to be of dimension -1. And if you form the fiber product in the category of smooth manifolds where you just get a point, it doesn't know that it has dimension -1. It thinks it has dimension 0. But in this world of generalized derived manifolds, the object that you get, in some sense, remembers that it should have dimension -1. What's that?
Take a function
Yeah.
levels common.
So let me hold that thought for a moment. Let me make a definition. Exactly because you want to have those resolutions. I think C infinity is the least structured case in which you could consider this and have it be a reasonable thing to do. Okay, so definition, a generalized manifold, let's say XOX is quasi-smooth if locally on X there exists a pullback square. Say XOX maps to some smooth manifold M, maps to a pullback square like this where, so you could either say this X looks like the fiber of a map of smooth manifolds over some point of the target, which is saying there's a pullback square like this. You could also say it fits into a pullback square like the ones that we were talking about a minute ago. So if you take diagrams of smooth manifolds, M0 and M1 mapping to M, you can always form the fiber product of such a diagram in this world of generalized derived manifolds. The quasi-smooth ones are the ones that you can get via this construction.
Why do we have a double arrow on the bottom line?
Oh, sorry, yeah.
Shouldn't be a double arrow.
Shouldn't be a double arrow. So these are the quasi-smooth derived manifolds. And now let's come back to your observation. So beware. The underlying topological space of a quasi-smooth derived manifold can be arbitrarily bad. Namely, anything that can occur as a closed subset of a Euclidean space can occur as the underlying topological space of something that appears via this construction.
Just closed, right?
What's that?
Like the zero levels of smooth functions, just anything which is closed.
I think anything that's closed is the zero locus. Yeah,
The Cantor set could have many structures OX.
exactly. So the Cantor set can have many such structures. So remembering the underlying topological space of this, or forgetting OX, loses your ability to say anything. And also, remembering X doesn't remember very much. So for example, any of these quasi-smooth derived manifolds has what you can call its virtual dimension, which, if it arises in this situation, is the dimension of the dimension of M0 plus the dimension of M1 minus the dimension of M. It would be the dimension of the fiber product if this was transverse. And the data just of this derived manifold knows what that virtual dimension is supposed to be. It's intrinsic in terms of this object. So, so now, well, you asked so this notion of quasi-smooth derived manifold, so, well, let me just come back to the intersection formula stuff. So let M be a smooth manifold.
Could you say what is the tangent complex here? Or?
Yeah, I could. It would be a little bit of a digression, but I can say it. Sure. Okay, so let's say you fix a topological space X, and now I want to consider, I don't know what I want to call this. So this is going to be the collection of all OX satisfying our axioms. So there's some, I should think of this as an infinity category. There's some infinity category consisting of all ways to make X, to give X the structure of a generalized derived manifold. So now let's say we,
It's not like an infinity topos or...
well, you can do this construction more generally when X is an infinity topos if you want to allow things like orbifolds in addition to manifolds. But that's a generality which is sort of orthogonal to what I'm talking about. Yeah. So, all right. So let's say we fix an OX, and then we can look at, well, how should I say it? Yeah, I guess I should say it like this. I want to look at the collection of all sheaves OX prime satisfying our axioms with a local map from OX prime into OX. Okay, so this is some infinity category. It's a place where you can do homotopy theory. And in this place where you can do homotopy theory, you can apply the construction which turns the category of spaces into the category of spectra. You can look at infinite loop objects here. Well, you get some, this is a place where you can do homotopy theory. This is a place where you can do stable homotopy. This is an example of a stable infinity category. Now, you can, and these worlds are related by constructions that you could call sigma infinity and beta infinity. And now you can take OX, which lives in this world, and apply sigma infinity to it. And you get some object that lives here, which I'd call the cotangent complex of x. But right now it lives in this sort of funny world. But now, if you want to understand what sort of object this is in more concrete terms, it's useful to replace these categories, which are hard to understand, by algebraic approximations, which are much easier to understand. So let me write sheaves algebraic of x. So this is going to be the category of sheaves of simplicial commutative R algebras. A with a map from A into the underlying simplicial commutative R algebra that you can extract from OX by just thinking about the real valued functions. So this is something that doesn't need the full structure of X as one of these generalized derived manifolds. It just needs to remember OX as some kind of sheaf of rings. And then you can consider exactly the same construction that you can do here. There's some, you can take this homotopy theory and stabilize it. And now, this is now in the world of algebra. And there's a general bit of algebra will tell you that this you can identify with the sheaves of OXR modules. This is something, it's really, like, let's assume, for example, that X is an ordinary smooth manifold, so OXR is just a sheaf of commutative rings in the usual sense. Then you can talk about sheaves of modules over it, and this would be its derived category. This would be like chain complexes of sheaves of modules over that commutative ring. What's that?
No finiteness conditions whatsoever.
No finiteness conditions whatsoever.
Finiteness results.
Right. Okay, so now you can, there's a functor from this hard category to this purely algebraic category, which just takes the idea that you can map X into any smooth manifold and remembers that you can map X into R. And that gives you a functor from between these stable infinity categories, and something which is probably not obvious. Theorem, this is an equivalence. So what's the upshot of that? Well, I guess you don't need to know that it's an equivalence to know that you can take this object and apply this functor to it and get something which lives in the derived category of OXR modules. And that object in the derived category I would also call the cotangent complex of X. So this is something you can define in full generality. You don't need any finiteness conditions on anything to define it, but in order to say something about it, you want to put yourself in a situation where this is a reasonably nice object. So for example, if X is a smooth manifold, this just produces the usual cotangent bundle. And if X is a quasi-smooth derived manifold, it produces something that can be modeled by a two-term chain complex of vector bundles. What's that?
Just two terms?
Just two terms. So quasi-smooth is terminology I use for like the analog of being a local complete intersection. So the class of quasi-smooth derived manifolds doesn't itself have fiber products. And if you want to enlarge it so that you do have fiber products, that enlargement is what I would call derived manifolds. Then the cotangent complexes of those sorts of objects you could see like arbitrary bounded.
You're not allowed, you take this point with this shifted.
Oh, yeah. And you cannot repeat it.
Well, so you can form this fiber product called the result X. X is not quasi-smooth anymore, but it still lives in this world.
But let me just tell you another way of reading this theorem.
Another way of reading this theorem is that if you have an OXR module in the usual algebraic sense, then it gives you some, let's say you have an object which I'll call M here. Then under the inverse to this equivalence, you can apply the inverse of this equivalence and then apply loops infinity. And then you get a new sheaf on X, which deserves to be called OX direct sum M. So the statement is, if you think of one of these funny sheaves, it's a sheaf on X where you remember that you're allowed to take sections of your sheaf and compose them with smooth functions from R to R to get new sections of your sheaf. And this theorem is essentially saying, well, if OX is such a sheaf and you take any OX module, OX plus M is also such a sheaf, because you can describe how you want smooth functions to act on this by differentiating the smooth functions to see how they'll act on the second factor. That's essentially what's involved in proving this statement here.
And I interrupted you. You were
Yeah.
going to
Oh, maybe I was going to go back to the original setting, I guess. So let's say M is a smooth manifold. And now let's consider, let's say I give you a map from X into M such that this is proper and the map is proper and X is a quasi-smooth derived manifold. So M has some dimension D, and X has some virtual dimension, which I'll call D prime. Then in this case, you can associate to this a fundamental class of X, which is going to live in H, I guess D minus D prime of M. And if I don't want to keep track of orientations, let's just say with Z mod 2 coefficients. And now, once you've made this definition, you can write a formula like this. If you want to cup the class of X with the class of Y, this is always the class of X cross M over Y, where this fiber product is formed in the world of derived manifolds. So this now holds with no transversality assumptions. So this is one answer to the question of what do these derived manifolds buy you. They buy you a formalism in which you can just say things like this, and they're always true.
You have simple isolated and you take hyperboloids that become a code or something like that.
Okay.
Then the only interesting part in that, for this formula, we have this plane, hyperboloids, they are hyperbolas, and then the intersection, and then all of a sudden they become two lines.
So R squared maps to R via X plus Y goes to X times Y. And this looks like it would be 0, and it would be that.
And then the interesting part is really like this example of the point over the point, isn't it? Or is we have here a point over a point.
Sorry, what do you mean?
Well, I'm just saying that this is this derived manifold behaves like this point over a point that you just. That's how, isn't it? Yeah.
I don't quite know.
Well, this derived manifold
Yes.
will have a structure sheet, and everywhere in the two lines will be concentrated at 0, so to speak, except at the origin where it's the example we saw, isn't it?
Where it's, well, I think it's, I'm not sure what you mean by it's the example that we saw.
Well, so how does the shape look in these two lines?
So it looks like it's not derived. It's a sheaf of sets in this case. It's I mean, you take the sheaf of real valued functions on R squared, and then you have this function x times y, which gives you a map of sheaves from this thing to itself. Then the structure sheaf of this guy will look like the co-kernel of that map. So asking whether or not that has any homotopy theory to it is asking, do you know any germs of smooth functions at the origin, such that if you multiply by x times y, you get 0? And the answer is no. Multiplication by x and by y, those are both monomorphisms. And so, I mean, this is a valid thing that you're allowed to form in this world of derived smooth manifolds, but the derived somehow doesn't add anything in the case of this example.
Okay.
When you're talking about the right category of sheets or modules, you're living in that, and you can consider like a more reasonable sheet like vector bundles. But for those, I assume that this would be just a homotopy category of chain complements. I mean, just chain homotopy quarter fullness classes, because there are no extensions.
Well, sorry, you're asking.
Okay, let me rephrase it. I'm really concerned about the fact that the range of infinite functions is kind of huge, so there's no hope of getting a given category of models for any practice condition whatsoever.
Agreed. Yeah.
But it doesn't matter for the derived setting, I suppose, because you just can consider.
I mean, there's a good finiteness condition in the derived category, which is being perfect.
Yeah.
And that condition, without any kind of Noetherian hypotheses, it doesn't survive taking well, even with Noetherian hypotheses.
But they don't want to do that anyway because we live in the derived system.
Right.
Another question, maybe a bit philosophical. Could you be a bit more algebraic about this whole theory? Just kind of redefine rings, like ring with an extra structure which would axiomatize the section of smooth functions, and then maybe look at those rings.
Yeah, I mean, so another way to describe this. All right, so there's
like 5 cases.
this notion that people call a C infinity ring. So definition. A C infinity ring is a functor from, say, smooth manifolds. Oh, no, why don't I say Euclidean spaces? This is the usual definition. Spaces to sets that preserves finite products. And now, so the C infinity rings form an ordinary category. And there's a construction that you can apply. The notation of my book is P sigma of C. So this is what you get by formally. Contains inside it sort of the free C infinity rings on finitely many generators. And there's a construction that you can apply to this, which is what you get when you take C0 and formally add certain kinds of colimits. It produces an infinity category, which, I don't know, let's call it C plus. It contains C as a full subcategory, and an equivalent way of constructing it is to take functors from Euclidean spaces to spaces that preserve finite products. That produces this same C plus. So you can think of this C plus as a non-abelian version of the derived category of C. It's something that you get. It's built out of simplicial objects in C, or it's modeled by simplicial C infinity rings, if you like. Okay, so then you can also define, if you look at this world that I call generalized derived manifolds. This sits inside a category where your objects are spaces X with a sheaf, let's say a C plus valued sheaf on X. So if you have a C plus valued sheaf, you impose some conditions on it, which are analogs of the axioms that I described earlier, and it will get you the same notion of generalized derived manifold.
But there is no way to construct X from a ring. There is no space construction.
Oh, there is, yeah. So there's a construction which takes, let's call it like the smooth version of the spectrum, which takes C plus to this world of generalized derived manifolds. And in this setting, because we're talking about smooth functions, it's very easy to make globally defined smooth functions. This hits almost anything you would be interested in. So like any compact derived manifold is in the image of this construction.
Or any reasonably nice open subset of such, but not.
Yeah, so
Statement along those lines is if you have
open set which has compact closure in something, then that open set is affine.
And it also has products. So we have a version of has a product specifically,
Yeah.
which corresponds to just to the product.
Yeah, this preserves all limits. It's a right adjoint to the global sections functor, just as in algebraic geometry.
Well, very nice. Thank you so much. Any questions from the students and the audience? Well, thank you so
No,
much.
perhaps some quite speculative thing. So one of the very nice applications of the intersection formula were Hopf invariants, right? So is there any way of constructing exotic Hopf invariants for something which is not quite a manifold, but some object in this setting?
All right, I don't know how to answer that question, but so let me answer instead a question which that makes me think a little bit of. So one question that you could ask about all this stuff is it really worth all this pain to have this generalized intersection formula when, after all, you know that whenever you have two non-transverse maps, you could always move them a little bit and make them transverse. So that is true, but there are contexts in which it's false. So for example, if you want to talk not about plane manifolds, but manifolds with the action of some compact Lie group, then you don't have transversality. It's not true that anytime you have maps of G manifolds, that you can always G equivariantly move them a little bit to make them transverse. So if you were interested in that setting, another way of saying it, this process of moving things a little bit to make them transverse destroys symmetry that you might be interested in. So if you would really like to preserve symmetries that you were interested in, if you would like to see in this setting where G was acting on everything, you want G to still act on the fiber product, then you probably don't want to make some non-equivariant perturbation, and this is an alternative thing that you could do. You could consider the derived fiber product, and that would in some sense still inherit an action of the group G.
And what about, in classical equivariant algebraic topology, there is some discrepancy between geometric and homotopy theoretic borders in theories. So
Yes.
if you try to do the analog here,
I think
you will get everything.
I think it will be relevant to that discrepancy. I mean, I think, yes, your intuition is correct that this will connect with that discrepancy. Flat family. Oh, like flat in the sense of algebraic geometry. Well, certainly, this is like derived differential topology. If you did derived algebraic geometry, the answer is yes.
No, question specifically about topology. Just
Well,
because what I can concerned about is that the underlying set seems pretty random, right? It can jump in a linear fashion and then
I mean, there's certainly a good notion of submersion.
there is a situation where you do this transversal information. Really change.
Yeah, well, versal deformation, that feels to me like a complex analytic idea, right? It's the finite dimensional versal deformation spaces are consequences of the fact that you have finite dimensionality for global sections of some compact space in complex analysis. I would not expect that to be such a great idea here.
So, which is the relation between derived algebraic geometry and derived algebraic topology?
So, one relation is the following. So you
Right,
could
what?
say, so we have a functor from smooth varieties for R, manifolds, which is the language of schemes. You take an R scheme X and assign its set of R value points. And now this world of smooth varieties over R sits inside some larger world of let's call it derived schemes over R. And let's impose some finiteness conditions on this. So derived schemes, it's almost a finite presentation. Well, I can ignore this if I'm just going to write generalized. So there's an analogous construction that you can apply to derived algebraic objects over R, and instead of producing smooth manifolds, it'll produce these generalized objects, and this diagram will compute. And if you can match finiteness conditions that you have here with finiteness conditions that you have here. I don't know if this is the kind of thing you had in mind.
Yes.
Any other questions? Well, thank you very much.